So I already have a video on 2.2, so this is 2.3, which is analyzing graphs of functions. And there's a lot of vocabulary and definitions in this section that are important for going forward. And so you're going to want to pay special attention, at least have all the vocabulary written down somewhere, whether that's because whether it's printing off these slides so that you have the definition somewhere, or rewriting it yourself. But there are going to be a lot of words, terms, and I've got lots of examples to go with them. So 2.3 covers a lot of material. It covers using the vertical line test for functions, finding zeros of functions, determining the intervals on which functions are increasing or decreasing, determining relative minimum and relative maximum values of functions, determining the average rate of change of a function, and identify even and odd functions. So there is a lot of material here, which means I have a lot of slides, and this is going to be a long one. So hopefully you got some food. I did not, so I'm going to be eating when I get done with this. Next time I'm going to have to plan around and be like, maybe lunchtime's not a good time if I have not eaten yet. So I'm going to start with domain and range. So domain and range, domain has been talked about several times. It was mentioned in P.5 when we were talking about rational functions, and it came up again in 1.1, and then we talked about it again in 2.2. We talked specifically about domain and range. So domain is the set of inputs, and then the range is the set of outputs. So when we start looking at equations and functions and graphs, when we find the domain and the range, we give our results in interval notation. And we use interval notation going forward for anything where you are giving a set of values. So everything we're going to do is interval notation. And so if you don't remember what that is, you can go back to section P.1. It talked about interval notation and how we write those things. So I have an example here. This is an example from the textbook. The textbook has this as one of their examples. I'm going to explain it in my terms. I think it might make more sense than trying to read the textbook and how that works. So we're going to start by finding the domain and range of the graph. So we have this graph here, and you can see that in red they've marked the domain and they marked the range. So the domain is all of the inputs. What I do when I look at these is I usually kind of put a graph. I highlight the parts of the x-axis where I have values, where I have x values. And that helps me do the interval notation, because interval notation is always off of a number line. So when I have the domain, I'm going to just look at a number line here. And the left side of my highlight here, the smallest x value that I have graphed is at -1, and they give you that value. So I have -1 on the graph. And then as far as the right, where I stop that is at 5. So I have everything in the x in between here, and then I have to pay attention to the dots. So on the left side at -1, it's a closed circle, which means that value is included in the domain. So if it's included, we use a bracket, and the bracket faces where we have shaded. Oops, did not want to actually draw. So I have a bracket facing towards the shading part. And on the right side, if we have an open circle, that means it's not included in the domain, which means it's a parenthesis, and the parenthesis faces where you shade. So that means that's going to face to the left. So that gives me my interval notation for the domain. So I just read it off of the graph. I have a bracket at -1, and then I stop at 5, and I have a parenthesis. So that is the domain. The domain is all values between -1 and 5, where -1 is included and 5 is not included. And I read that off of the graph, where I have basically highlighted all sections of my x-axis where I have graphs above it or below it, basically. When I do the range, I do something very similar. So I'm going to also have a number line. And I'm going to do the range here in a different color. So the range, I'm going to look at my lowest value, of the y, the lowest as low as it goes, which is that you can see the label point 2, -3. So that's the lowest part of the graph. And then I have a graph everywhere in this section all the way up to 0, 3. So that's the portion of the y-axis where my graph exists, basically, is along that green line. And so that's the range, the output. And so we read it from the smallest value to the highest value. So the smallest, the lowest value on that y-axis is -3. So I have -3 is the low point, and then the highest value it goes is +3. So that's going to be 3 on the high point. And so I have graphed everywhere in between -3 and 3 on the y-axis, because the range is the y. And then I have to look at my ordered pairs again in the circles. So on the low end, you can see there's a closed dot. That value is included. So that means I have a bracket at -3 facing where I'm shading. And then on the high end at 0, 3, there's a closed circle, which means it's included. So that is a bracket, and this one's facing to the left towards the shaded part. So my range here, when I put this in interval notation, is a bracket at -3 to 3 with another bracket. So it's all values between -3 and 3 on the y-axis. These are y values, and we're including the endpoints. So the domain is the x, the range is the y. And I translate these to number lines so that I can get the interval notation. Are there any questions? Okay, so I have another example here, a different type of graph. So on this graph, I have a closed circle on the left side, but if you look at the right, there's no closed circle. So that means that it goes on forever. So if there's nothing there, no circle open or closed to stop it, we assume that it goes on forever. So that I usually just put a little arrow there to indicate that. So let's start with the domain, and I'm going to do the same thing. I'm going to put a number line, and I'm going to put my 0. So I'm going to highlight where I have x values, basically. So I have my graph is the furthermost point. I'm going to kind of guess here. It looks to be right there. And then I have my graph. And then because it goes on forever with that arrow, that means we also go on forever towards the arrow on our x-axis. So if there's an arrow, then it also is the same way as the x. So my domain here is, and I'm going to have to estimate here because I don't know the exact values, but it looks like if our horizontal axis, the x-axis, is counting by 2s, so it looks like we're halfway between a tick mark, which would be -1. So it looks like I've got -1, and then I'm going on forever with x values because of that arrow. So my number line is going to be -1, and then it's going towards positive infinity. So we have a closed circle at -1 on the x. The point looks to be about -1, 4, if I want to label that this -1, 4. So our x value there is at -1. We have a closed circle, which means it's included, so that's a bracket. So the domain is a bracket at -1, and then we go to infinity, which always has a parenthesis. Next, I'm going to do the range, and where I'm going to do the same thing. I'm going to have my number line. And I'm going to first highlight where I have things graphed as far as y values. So it looks like the peak is at about 7 on the y-axis. And then because of my arrow, I go on forever going down. So, and down are small numbers. So it looks like I've got 7. And then I'm heading towards negative infinity because I'm going smaller numbers. So down is to the left if you're looking at a number line, towards the negative numbers. Now I don't have a circle at that high point here, which looks to be roughly 2, 7 if I'm estimating that. There's no circle, but because there's no open circle, we're assuming that it's included, which means that's going to be a bracket. So it's going to be a bracket unless there's an open circle. So I have a bracket at 7 facing where I'm shading, facing towards the negative numbers because our graph is going towards the negatives. So when I read this, I have a parenthesis in negative infinity, because infinity, that symbol always has parentheses. And then I go to 7 with a bracket. And so that's my range. My range is negative infinity to 7. So we always go from the smallest number to the highest number, which in the case of the y-axis is down to up, while with the horizontal it's left to right. Are there any questions? Okay, so the next thing is the vertical line test. And so this basically is if you can draw a vertical line through all points, any x point on the graph, any point, and you only hit the graph once, which means you never hit it more than once, you have a function. So there's 3 examples here. So on the left, I can draw a line right here, and I'm only really, it looks like I might be hitting the graph. Let's say I'm hitting the graph once. But if I draw a line where I have the red dashed line, I'm hitting the graph twice. So because that vertical line goes through the graph twice, it is not a function. Now the middle one, you can see there's a vertical line, a dashed line, and it goes to the graph once. And it doesn't matter where I draw that line. I can draw one right here. No matter where I draw it, and I can just draw lots of them, I'm only ever going to go through the graph once. So that makes this a function. Now the third one here, we have a line, we're not going through the graph at all, but that's fine because you just can't hit it more than once. So you can hit it 0 times, or you can hit it once if I draw lines in other places, but you never go through it more than once. So that means that it's a function. So that's the vertical line test to determine whether something is a function or not. You just basically look at, is there any spot where if I draw my line, I hit the graph more than once? If so, it's not a function. Otherwise, it's a function. The next term we need to talk about are zeros, so zeros of a function. So the zeros of a function are all locations where the function is equal to 0, where your y value, your f of x, is equal to 0. So that means if y is 0, that's an x-intercept. So all of your x-intercepts are zeros. Y-intercepts are not zeros because y-intercepts, the y value is not 0. And we can have zeros that are not x-intercepts if you get values that are complex numbers. So you could have zeros that are complex numbers, but they're not x-intercepts because we don't graph complex numbers. And so they don't intersect the x-axis. So here's an example where we are going to find the zeros. So to find the zeros, you have this function f of x equals 3x squared plus 22x minus 16. So you start by setting that equal to 0. So you replace f of x with 0. So we have 3x squared plus 22x minus 16 equals 0, or 0 equals that. So now you need to solve. So that is section 1.4, so you could try to factor it. You can try to use the quadratic formula. You could do completing the square if you want, but I usually either factor or try to do the quadratic formula. So if you don't want to try to guess and check with factoring, and when I have numbers like 22 and 16, I usually would rather just do the quadratic formula. So that's what we'll do. So I have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's the quadratic formula. I'm going to rewrite my square root. And now we are going to plug in our actual numbers. So b is the middle term, 22. So that's going to be negative 22 plus or minus. And then I have b squared, so that's 22 squared minus 4 times a, which is in front of the x squared term, so that's 3. And then times c, which is the constant term, negative 16. And then in the denominator, there's 2 times a, which is 2 times 6. So I'm going to take my calculator and I'm going to start following the order of operations by simplifying this. So I have negative 22 plus or minus. 22 squared is 484. And then negative 4 times 3 times negative 16 is 192. So I'm going to add 192 because I have two negative signs there. I have the minus in front of 4, which is a negative, and then the negative 16. So those cancel, those become a positive. And then in the denominator, 2 times 3 is 6. So now I'm going to just move to the next line here. I have negative 22 plus or minus, and then I'm going to add inside my square root the 484 plus 192. That's 676, and then I'm dividing by 6. So now I'm going to see, does 676, if I take the square root, do I get a whole number? If I don't, then I need to simplify the radical there. But if I do, then that's great. And 676, actually, you can take the square root of that, and that gives you 26. And because we got a whole number, that means we could have factored this if we wanted to. So I have x equals negative 22 plus or minus 26 over 6. So now I'm going to split that into two separate equations, one with a positive and one with a negative. So I have x equals negative 22 plus 26 over 6, and x equals negative 22 minus 26 over 6. So for the first one, negative 22 plus 26 is 4. So I get 4 over 6, which is equal to 2/3. And that's one of my zeros. And then in the second equation there, negative 22 minus 26 is negative 48. And negative 48 divided by 6 is negative 8. So that's my second zero. So when it says to find the zeros, you're finding where your equation is equal to 0, and then you're solving. And so because we had a quadratic, we needed to use techniques from 1.4. And so I chose to use the quadratic equation. And so I got two zeros, 2/3 and negative 8. Are there any questions? Okay. I have another example of finding the zeros, and this one's a rational equation or function because we have a fraction with a variable in the denominator on the right. So we want to find the zeros. So it's the same rule. Your f of x is equal to 0. So I have 0 equals x minus 9 over 4x. And now I need to solve for x. So to do that, you want to multiply both sides by the denominator. So I'm going to multiply both sides by 4x. Now 4x times 0, anything times 0 is still 0. So I have 0 still on the left. And then on the right, I just have x minus 9 because the 4x times 4 in the denominator cancels out with the 4x that I multiplied by. So those cancel, I'm just left with x minus 9. So to solve for x, I just add 9 to both sides, and I got 9 is equal to x. And so I have only one 0 in this case, x equals 9. Any questions? Okay. And now this one is not exactly, oh, Colleen, I see you're typing. Let me go back. I kind of moved ahead a little bit too much. This is part of functions. So this is part of section 2.3 where you're finding the zeros. So you're finding the zeros of functions. And to do that, you take your function notation, the f of x, and you set it equal to 0. All right. Now, my fifth example here, this isn't exactly finding the zeros, because here we're looking for where f of x is greater than or equal to 0. So we're finding the zeros and where it's greater than 0, which means positive. So this is basically saying where our y is equal to 0 or y is greater than 0. So we're looking for, if you were looking at your graph, we want all the positive y values. So everywhere we're above the y-axis or on the y-axis, basically. So when you're looking for the intervals where f of x is greater than or equal to 0, that's what you're solving for. And so it says to graph f of x equals x squared minus 4 and determine the intervals for which, we're greater than or equal to 0. So I'm going to pull up Desmos and start graphing. Okay, and to type enter our functions into Desmos, you type it just like you see it. So I have f parenthesis x parenthesis equals, and then my equation was x squared minus 4x. And so this is what our graph looks like. And what I'm going to do is I can share this graph. I am going to export the image, and then what I usually do is just copy image, and then I'm going to, if it will let me, if I can find my mouse, will let me paste it here. No, I was hoping I could just paste it. Let me briefly stop sharing, and then I will paste that in. I'll have to stop the slideshow, and then I'll open it back up. And you're looking at my ceiling right now because I put my tablet on the ground. So that's what you're looking at. No worries. Okay. Start slideshow again. Start sharing again. It's taking a little time. There we go. Okay, so now I've pasted it in. So that's our graph. So I use Desmos to graph that. And we are looking for the intervals for which we are above or equal to the x-axis. So we're equal to, looks here at 0. And then according to that graph, it looks like at 4. And then we're above it. So if we look at this, this is very similar to how we did the domain, where we have little arrows there if there's no circles. So when we give the intervals, we're always giving intervals in terms of x values. So we are looking at intervals of the domain. So I'm graphing, because it's the left part there, the negative x's, that has our y values above the x-axis. But because of the arrow, I'm going on forever. Then at the right side at 4, x equals 5, you can see we're in the positive part. We're in the top half of the graph. And so those are all positive, greater than 0. And because of the arrow, we go on forever. So we always give our answers in terms of the domain. So, oops. What I really should say is give answers as intervals over X, which is the domain. So I'm going to make a number line here. And I have 0 and 4. Those are the two spots where I'm equal to 0 according to my graph. And then I'm shading the left and right of each of those. And if they're equal to 0, that means I have brackets. So I end up with two separate sections, which means we have two intervals. So we are greater than or equal to 0 from this interval that goes from -infinity to 0. And that's the left side. And then we are also greater than 0 from 4 to infinity, the right side. In between 0 and 4, we're actually negative. Our graph is below the x-axis, so our graph is negative. And we want only the ones where we are positive. So we have two parts where we are positive. Are there any questions? Okay. So the next topic is increasing and decreasing functions. And so we always look at these going from left to right. I have the definitions here, but the graph makes more sense. You're decreasing if you're going from left to right, it's going down. It's constant if from left to right it's straight. And then it's increasing from left to right if you're going up. So we always read from left to right when we're looking at these to figure out if things are increasing, decreasing, or constant. So I have this graph here, and I'm going to be reusing this graph for several examples. Determine the open intervals. So open means you're using parentheses. You're not going to be using brackets. So open intervals on which the function is increasing, decreasing, or constant. So if you look at the graph, there's no dots, so that means that these are going to go on forever. So I can put little arrows there, so that will remind me that these are going to keep going. Now, just like when we were finding the domain, and just like when we did the greater than or equal to 0 part for f of x, we always give our answers in terms of x. So give your answers over the domain. So you're always looking at the x values where this is occurring. So I'm going to do different colors for increasing, decreasing, and constant. So I'm going to do increasing here in yellow. So that means if I move from left to right, I'm going up. So I have this increasing part over here. So when I translate that to the domain, it is all numbers that are less than 0 or equal to 0 there, but we want open intervals. So those are all spots where I'm increasing. And then according to the graph, I'm increasing again for this part. And that starts at 2 on the x, and then that goes on forever. So we are increasing. And if I draw my number line, I have 0 and 2 as the kind of endpoints there. And I am increasing for all numbers that are less than 0, and then all numbers that are greater than 2. Oops. So, and these are open intervals, so I need to use parentheses. So that means I'm increasing from -infinity to 0 and from 2 to infinity. So next is going to be the decreasing. Where are we going down? So I'm going to do that in green. And we're going down in between those two parts from 0 to 2 right here. So that's the part where our graph is decreasing. So I'm going to make my number line. And I have 0 and 2. But our graph is going down in between 0 and 2. So it's going down as you move from left to right. And we want open intervals, which means parentheses. So we are decreasing from 0 to 2, and we have parentheses. It looks like an ordered pair, but by context of the question, you know that's an interval. And then when it says constant, you do need to still answer whether it's constant, because otherwise we could think maybe you just forgot to answer that. So the constant part would be where is it flat? But we don't have anywhere where it's flat, so we just write no constant intervals to address the fact that you did consider that, but there aren't any. So there's nowhere where we are flat and horizontal, so there are no constant intervals. We only have increasing and decreasing intervals. Are there any questions? Okay. Next are relative minimum and relative maximum values. So we don't include endpoints here. So I'm going to just make a note. So if there has anything with where it stops, we don't look at those. We only look at within when it's separate. It's like has other parts on either side of it. And so I've got a graph here. Minimums, relative minimums are the low points, and maximums are the high points. So you could have more than one low point, more than one high point. So you can have more than one. A relative just means it's the highest or lowest part in its area. If it asks for an absolute, that would mean the highest one and the lowest one. But relative just means it's a peak or a trough, so the low or high point in the general area of the function. So the same graph here, we're looking for relative minima and maxima. And so if I highlight here, first one is minima, all the low points. So I have just one, which is here at net 2, negative 2. We don't include the endpoint. You can see it goes lower than that, but we don't include those endpoints. So we have a minimum at 2, negative 2. Sometimes we say the minimum is negative 2 at x equals 2. That's another way to write it. And then if we look at the maximum, let's make that green. The maximum is the highest point, and so I only have one of those at 0, 2. So we have a maximum at 0, 2, or you can say the maximum is 2 at x equals 0. So you're just labeling where it's a maximum or minimum in the kind of the neighborhood of the function. Any questions? Okay. Next is average rate of change. We're almost at the end of all of these definitions. So the average rate of change is basically you're finding the slope. You're finding the slope between 2 points. You basically draw a line between 2 points, and then you find the slope of that line, and that is called the average rate of change. So they call that line the secant line, so you can see on the picture what that means, which means you can find the slope even if your graph is not a line. And so the abbreviation is M, and then it says, this is not second, but that stands for secant. And they use m because it is basically just a slope. It's just a slope of a different kind of line. So when you're finding the average rate of change between two things, you just use the slope formula. So in my example here, find the average rate of change of f of x equals x squared minus 2x plus 8 from x equals 1 and x equals 5. So we need to find our function values, f of x sub 1. That is, this, we basically plug in, that's plug in f of 1. So I need to plug 1 into my equation. So I need to first figure out what that function value is. So 1 squared is 1, minus 2 plus 8. 1 minus 2 is negative 1 plus 8, that's 7. So this gives me an ordered pair of 1, 7. Now I'm going to do the same thing for x2. And x2 is 5, so I'm finding the function value at 5. So I plug that in for x. So that's 5 squared minus 2 times 5 plus 8. That's 25 minus 10 plus 8, which is 25 minus, let's see, negative 10 plus 8 is negative 2, so that's 23. So then that gives us 5, 23. So now we have two ordered pairs, and we're basically just finding the slope. It's the same thing as y2 minus y1 over x2 minus x1. So I have 23 minus 7. Those are my y values. That second point is the y2. And then the x is 5 minus 1. So 23 minus 7 is 16. 5 minus 1 is 4. And then 16 divided by 4 is 4. So our average rate of change is 4. So it's just different terminology. We can't call it the slope because it's not a line. So we just call it average rate of change, but it is basically you're using the slope formula. Any questions on that one? Okay. And this is the last topic that's in 2.3 is even and odd functions. So if you remember back in section 1.1, we had symmetry. That was in the week 2 assignment, and you had to test whether it was symmetric with the x-axis, the y-axis, or the origin. When we talk about even and odd functions, those are related to symmetry. So an even function is symmetric with respect to the y-axis. So that would be if I have something that looks like that. So across the y-axis, it's, well, I can't draw a mirror image, but it's supposed to be a mirror image there. An odd function is symmetric with respect to the origin. So that would look something like this, where they're not exactly mirror images. You have to reflect it once and then reflect it again. That's symmetric with respect to the origin. And if there's no word for symmetry across the x-axis, that's not even or odd, it just doesn't have a term. And so the tests for even and odd functions are the same as the tests for the x-axis symmetry and for the origin symmetry. So you're using the same tests as before. We're just applying a new language to it in terms of the function itself and not just an equation. So this is my last example. Determine whether g of x equals x cubed minus 5x is even, odd, or neither. Then describe the symmetry. So if we go back for both of these to test the even or odd, we have to plug in negative x. So that's what we're going to do. We're going to plug in negative x and then see what happens if we get the same function out. So I need to find what g of negative x is. And so I'm plugging negative x in for x. So I have negative x cubed minus 5 times, oops, that should be negative x. I need to make sure I remember that. Okay. So now I'm going to simplify the right side. When you cube a negative, your answer is negative. Any odd power with a negative gets negative. So that's going to be a negative, and then x cubed. Then negative 5 times negative 1, or negative x. Those negatives cancel, we get 5x. So I have negative x cubed plus 5x, and that's g of negative x. So if we look at our symmetry, if g of negative x equals, if we look at, or f of x, negative x equals f of x, if you get the same function, it's even. We did not get what we started with. Negative x cubed plus 5x is not g of x. This doesn't match what we started with. This is not g of x, so we know that it is not even, because we didn't get what we started with the original function out. The next thing is to test odd. Is it the opposite in sign? Is it negative and then your function? So negative g of x would be putting a negative, and then we have x cubed minus 5x. You distribute that negative, you get negative x cubed plus 5x. So that matches. That is equal to g of negative x. Those things are the same. My g of negative x, which is negative x cubed plus 5x, negative x cubed plus 5x, that's the same as negative g of x. So because those are equal, that's our rule for odd. So that means this is an odd function. Oops, I want my pen, not my highlighter. So we know this function is odd. If this test had failed, then your only remaining choice would be neither. So we know this is an odd function as such to describe the symmetry. So I'm going to go back to my notes here. And an odd function is symmetric with respect to the origin. So that's my symmetry. Symmetric with respect to the origin. And so if you graphed this function, you would find that it would be you would see reflection across the origin, or the line y equals x essentially. I should still have Desmos up here. I can graph that. So let's just graph this function so you can see this. G of x equals x cubed minus 5x. And so this is symmetric across the origin, which means I'm going to graph the line y equals x, and then I'm going to dash it. So you can kind of see that if you draw that line, you can kind of get a mirror image if you're looking at it in a way that it's sort of reflecting here, and then it's kind of reflecting here upside down. So that kind of helps you visualize whether it's reflection across the origin there. That helps me at least if I just draw that line there so I can kind of look at it. But basically, a reflection across the origin means that, say you take one portion, like let's say the negative portion here, you flip it upside down, so that would be down here, and then you flip it across the other axis, and that's here. And that's how you can kind of test your origin. It's a little harder to visualize, so that's why I do my y equals x and kind of see if it like sort of forms like a little pattern there. So that is symmetric across the origin, and that is what we call an odd function. So you guys have any questions on this example? Okay, are there any questions in general? I know I've covered a lot of things. This section has a lot of vocabulary, and I would not be surprised if you need to watch this a second time, maybe while you're doing the homework, just to verify. Nothing? No questions? Don't be afraid to ask me questions later. um, yeah, okay, Colleen, I see you're typing something. Yeah. You'll definitely be watching it again. Yeah, I mean, it's a lot to process at once. There's a lot of material, but that's why I record these. So, and I really think as you work through like practice problems, if you watch it and then try to do it on some practice problems, that will help. I picked from 2.3, the problems that the examples I did were the evens, so you can find some odd ones that are similar, and then you can check your answers with the odd problems. So thank you guys so much for joining, especially during lunchtime. I really appreciate it. This should be out in the next hour or so. I'll add it to the classroom, add it to mine. I'm going to make sure I eat my own lunch first, and then I'll put everything out. And then if you're subscribed to Remind, you'll get a message when it's up there with the PowerPoint and everything. So thank you guys very much. And I hope you're having a great Friday. I hope you guys have a great weekend. It's daylight savings is ending this weekend, so you get an extra hour of sleep between Saturday and Sunday, so that's going to be awesome. So I know I'm looking for that extra hour. So I will talk to you guys later. Thank you for joining.